Good morning. So today we are going to conclude the module that what we are doing, steady state cornering, and then looking at your handling characteristics. There are various handling tests. What we looked at is constant radius test, constant speed test, and constant steer angle test. These are all called open loop tests. So you drive and then look at the behavior or response of your vehicle for the given steering input. And you are going to rank the vehicle based on that. So for comparison of vehicle and their performance in cornering, lateral dynamics, we do such kind of study mathematically with the viable models like bicycle model or accounting suspension, and then we have looked at roll of suspension, vehicle roll, and hence what would be the effect on understeer gradient and so on, that we have done a very wider spectrum of understanding of lateral dynamics with the help of bicycle model and model with the suspension. We have done a lot of learning so far. And currently, what we are doing is we are looking at the steady state motion in a cornering, hard cornering, particularly maybe mid or high speed cornering. You see that understeer gradient of a vehicle play an important role. So initially we understood the understeer gradient primarily caused only from the tire compliances in the front axle and the rear axle. Why? Because the model what we consider is bicycle model, where we do not discretize the vehicle mass, and we consider the same mass, and the front axle wheel collapsed and considers one axle and the rear axle considers one axle. So the equation, fundamental governing equation of your steady state motion is a simple equation that emphasizes on the requirement of steering angle given by delta equals 57.3 into L by R degrees plus alpha F minus alpha R. So this is the fundamental governing equation for steady state motion that we have considered. In that model today, we are going to account if I consider the drive forces on the wheels. So what would happen? Drive forces on the wheels, what would happen? What would be the influence of the driving force on the understeer gradient is what is today's class objective, and that we are going to look at it. And in the previous class, we looked at an advanced model from the bicycle model, where we have accounted your suspension, and then we looked at the lateral load transfer that is going to influence your understeer gradient. And then also we looked at another important lateral force called a camber thrust in the last class. That is because of the change in camber, because of the roll of your vehicle body. Is what is influencing the understeer gradient. So in the last class, we looked at that. And also we looked at the role of your vehicle also going to give a kind of a steer effect on your wheels. And that effect is what is called a roll steer effect. And we have looked at that also in the last lecture. So today's lecture, we are going to look at the effect of tractive force on cornering. And for that, I'm going to take a model now, again, our good old bicycle model. I'm not going to consider suspension for the moment. That means there is no lateral load transfer consideration in today's discussion. Rather, instead of steady state motion, I'm going to put forces in front axle as well as in rear axle, considering all-wheel drive vehicle. So I will have a drive force. So when will you have a drive force? Why was it not there in a steady state motion? If I ask the question, it is pretty simple and straightforward that you would answer that forward speed is constant in steady state motion. So there is no acceleration. Hence, there is no tractive force or drive force in the front axle. And you would say that during the test, we don't look at the behavior by applying braking. So when you apply braking, then there can be deceleration, then there will be change in forward speed, and that would again bring in the braking force into the drive axle. But these two were not considered in steady state motion. The steady state motion only velocity was lateral velocity, and that also is very minimal. That won't drag your vehicle along the center of curvature. Rather, it will have a resultant velocity, forward velocity to the longitudinal axis at an angle called body slip angle, and so on. This is all what we have learned so far. So today's class, I'm going to take again a bicycle model back without considering suspension, but accounting driving forces onto that, and then see what is its effect on understeer gradient. Is that clear to all of you? So let me share for that my screen. So you're able to see the screen. And today's lecture is lecture number 30. And today's date 22/10/2021. What is that you're going to study is the effect of tractive force on cornering. So this is one step forward from the steady state motion. So what is that we are going to consider again is the bicycle model. So let me draw a model description for today's class. And this wheel represent a rear axle, two wheels collapsed and represented. And my front axle wheel is somewhere here. And that has been given as steering input because during the hot cornering. So my tire has been tilted somewhat exaggerated angle. That's for our better understanding. I'm drawing it here. So now this is what is my wheel plane. So this angle is what is steering angle delta, right? Steering angle delta. And now you know that I would have the slip angle developed. So that slip angle would be somewhat this, which is with an angle alpha f here. So if I ask you, what is this angle here? So that angle will be delta minus alpha f. Delta minus alpha f. You would take like that. The sum of this angle, right? So that let us take delta plus alpha f. Is that clear? Why? Because you follow SI coordinate system. So the angular measurement clockwise is positive, counterclockwise is negative. So I just count it like this: delta minus this angle to do minus this I put. So I get this is what is my angle here represented vectorially. So when I substitute here the value, I'll put minus, and that would account this angle. So I take it like that. So this is this angle here, right? Now, you know that the entire vehicle would turn about instantaneous center of rotation. So if this is the direction of velocity here, instead of along the wheel plane, it is going at an angle, slip angle, the slip angle generated, I would have my center of rotation somewhere on this line. And I know now my vehicle velocity slip angle is going to be here with some angle here. So instead of having it here, it can also be sometime here, depends upon its magnitude. So this is angle beta, my body slip angle, and this is my velocity. So if I draw a perpendicular from there, and that would meet, see, I'm just bringing in, I draw this deliberately the bigger angle so that I can confine this point in my screen. If you look at this turning is on 30 meters road, I cannot accommodate that here. So that is broken here, that's broken here, and it is meeting here like that you can see. So to bring in here, I take these angles, whatever I'm representing, a larger angle, but they are very small angle. So cos of that angle is 1 and sine of that angle is angle. So that we have already aware of it. So if this is my ICR and if this is my vehicle representation CG, and this is my rolling radius, the radius of curvature of my track, and I would have now, by joining this line to this and correspondingly perpendicular to that, velocity. So this is not force vector. This red, blue one, whatever I have drawn, all are velocity vectors. right? I can resolve one along the longitudinal axis, that is what is small u, and then one perpendicular to that, that's what small v, lateral velocity. But now here it is, this velocity is called forward velocity or vehicle velocity, vehicle speed, forward velocity, right? So now let me show in this the forces. So what are the forces? Already we know that the force one would be acting in the lateral direction. That is along this line, because this is the line about which turns. So you would have here this force is F, Y, F, right? And you would have here force. In a earlier, we have taken this all parallel to vertical because of those angles. But I'm taking exactly, if this is the direction of velocity, this would be the direction of this force. I'm taking like that, Fy, R. So these are the lateral forces in the tire. And now I have to consider my drive forces. So the drive force I'm going to consider along the wheel plane of the tire. It is not going to be acting like that. Along the wheel plane, it will be acting. So let me use the different color for to represent my drive force. So that is this force here. So this is the force here in the front. And that is F X. Look at the subscript X, F. And similarly here, I will have along this. That is Fx R. The subscript R refer to the drive force at the rear axle. So if I have these Fxf as well as Fxr, that refer to what? All wheel drive. All wheels drives. So if I have only Fxf, then it's front wheel drive. If I have only Fxr, then it is rear wheel drive. So I'm taking a general case, it is all wheel drive. So this is what are the forces at the contact of the tire wheel assembly with the road, and these forces are necessarily developed along with the lateral force. Now this drive forces as I am accelerating during hard cornering, and then I am going to see the effect of this tractive force on cornering. Right? So that's what. Now, is there any difficulty for you to understand this diagram? If you do not have any difficulty of understood, I will consider, and we will go ahead with the equations writing. So now what are the equations, governing equations? Governing equations are here, I will have in the front axle, there is a load, and the rear axle, there is a load. So there will be a centripetal force from the front axle, and that would be equal to the balancing the component of forces along the direction. So let me write first equation, WF into U square by RG. That is what is centripetal force, and that force, or I'm applying Newton's law. So this is my effect force, because of that the motion, and that would be given because of the force components of this along which direction? Along the lateral direction, along the lateral direction. So how do I get that is what now I'm going to explain you. Right. So let us consider now in the front I'll have Fy. Let me write the equation then explain it. Fyf cos of angle delta plus alpha f plus Fxf. I have this force and this force, Fxf into sine of delta plus alpha f. So the forces along the lateral direction, along this line and this line is what is that is causing this, right? So if that is so, you should see like this. The direction, no, let me just draw. I have just drawn the component. Please recorrect this direction of this, right? Here as well. So when it is lateral force, that's lateral force That's lateral force for the tire, right? So I should draw it like this because the angle, how this equation I have written to understand, you require this. Let me extend this line. That is the line of radius of the turn. This is also like that. Let me extend this line. So now let me show where is that force acting. So the lateral force here would be in this direction, perpendicular to the wheel plane. So this is Fy R. And here, perpendicular to this wheel, that is here, this wheel plane. So this is right. So this is Fy F. So now, if this is perpendicular to this, now whatever this angle that I have is what is the same angle here. That's what you should understand. This angle and this angle are same. And similarly, whatever this angle I have here, that angle is what? Alpha R. And that angle and this angle are same. Alpha R. So now you look at, I needed this force is along this line, centripetal force because of the front axle mass along this radius from this contact center. And this force is not along the line. It is at an angle here. This angle is what is our delta plus alpha F. So what is the component along this is what I have to take it here. And that would be cos component. That is how this term comes. So you follow that. And similarly, now here you see, along this I have to get, along this parallel I should get. So what would be there here? Again, look at for this force. Let me just extend this line back here. So this angle here, whatever is there, that angle is what is again delta plus alpha F. And its component along this direction would be the sine of angle. So this is its sine component. This is the sine component. So this sine component is opposite to that. That is why Fxf sine delta plus alpha F. So this term also you understood. So this is equation number 1. So what is my equation 2? That is centripetal force at the rear axle wheel contact at the road. So that is WR into U squared by RG. And that's going to be equal to, now here I have FIR. FIR is for the wheel plane perpendicular, but my the force, the velocity is in this direction because of slip angle. So the component of this force along this line I should take, along this line I should take. So that means I have to project on that. That would be FYR cos alpha R plus the direction here towards this is positive. So this is positive direction. And you look at now FXR. So FXR to get, I will extend this line here. So this angle is same as that of this angle, that is alpha R. So this is my component. So this component here is FXR sine alpha R. FXR sine alpha R. So that's my second equation. So if you have understood these two equations written clearly, that's all. It is done. It is very simple now, just a manipulation of equation to get what we wanted. Right. So what is my governing equation of my steady state motion? I'm taking bicycle model. I'm writing my steady state motion. In that, I'm going to substitute my slip angles, which is influenced by the drive forces. Yeah, there are some doubts somebody is asking. Yeah. What's the doubt? Someone is prompting. You have any doubt? Okay. So these are the two equations. And the fundamental governing equation is delta equals 57.3 L by R. I'm writing in degrees. That is why this factor I'll already explained you. This alpha F minus alpha R. This equation from Gillespie. The Wong textbook we referred at the beginning, where it is minus alpha F plus alpha R minus sign would be accounted because of the sense of thing. They are one and the same. Don't get confused. Right. So this is that equation now, our governing equation, good world Roman letter 1. And I'm going to substitute in this alpha F and alpha R. That I'm going to get it from here. That I'm going to get it from here. So like again here, I would consider my Fy F equals, since I take here an absolute value, I will take here C alpha F into alpha F, like that only. I don't get minus sign here. If I have minus plus here, then it will be accordingly changed. So if I take here plus, I don't put minus sign here. If I put minus plus here, then I will change here the sign. That's only the difference here that you to understand, you know that. And FIR would be C alpha R into alpha R. So this, knowing this, I'm going to plug in into equation 1 and 2. And my equation 1 is going to become now as WF U squared by RG on the right hand side. That's equal to here FI F. So FIF will be C alpha F into alpha F. And the cos of this angle. So what does that is this all angle delta, alpha F, beta, no, all are very small angle. If our reality is some 30 meters or 50 meters in the roving ground. This is a very small angle. So that is very small angle. Cos of this angle is 1. So this will be simply this term. And the second term, this would be F X F into delta plus alpha F. Sine of angle is as it is. So this is my equation. So now let me just rewrite this equation. See, I have here a delta term, right? So let me rewrite this equation. How I just want to write an expression for alpha F from this. What is alpha F? So that I can plug in this equation. So how do I do that is in this way. So here the term without alpha F would be taken on the other side first. So that is WF U squared by RG. So the term here is FXF into delta that comes on this side. That's going to be FXF into delta, right? And here what will I have? C alpha F plus FXF alpha F. And in this, if I take C alpha F, sorry, alpha F, C alpha F, if I take it out, this is going to be 1 plus FXF by C alpha F, and I take alpha F out. So now I can write what is my alpha F. So therefore, alpha F would be, so this entire term, I'm going to bring it down here. So when I do that, it is going to be WF by C alpha F into U squared by RG. U squared by RG. Sorry, so let me, afterwards I'll do that. I'm just going to take this down. So let me have this equation as it is, and 1 by C alpha F into WF U squared by RG minus Fx delta Fx delta into 1 by 1 plus Fx by C alpha F. Right. So this is my alpha F. So I can rewrite this equation for a convenient way so that it is easy for grouping the terms. So it will be take C alpha F inside. So that's going to be WF by C alpha F into U squared by RG minus Fx by C alpha F into delta into 1 by 1 plus Fx by C alpha F. So this is what is alpha F. Now that's my equation 3. That's my equation 3. So similarly, I can get my equation 2 modified now. My equation 2 would be what? When I substitute FYR is equal to C alpha R and alpha R into equation 2, into this equation 2, and then considering the smaller angle effect, I would be able to rewrite this equation 2 for alpha R. So that would be WR U square by RG. On the other side, right hand side, I had FYR, that is going to be C alpha R into alpha r plus cos alpha r become 1. So plus fx r and sin alpha r is alpha r. Alpha r. And now in this, let me take C alpha r out. C alpha r out and alpha r out. It's going to be 1 plus fx r by C alpha r into alpha r. So what is WRU squared by RG? So now this equation can be again rewritten as when I bring this on this side, it is WRU squared by C alpha r into RG. This side it is 1 plus fx r by fx r by C alpha r to alpha r. Therefore, alpha r is going to be WRU squared by C alpha r RG into 1 by 1 plus fx r by C alpha r. So this is my equation 4. So now I have alpha r term. I had here alpha f term. So I can substitute for alpha f and alpha r now in equation Roman letter 1. So let me do that now. So by substituting, how that would be changing? So what is my equation? Delta equals 57.3 L by R plus alpha f minus alpha r. So this is going to be delta on this side 57.3 L by R plus, now my alpha r substituting would become here WF by C alpha f into U squared by RG minus FXF by C alpha f into delta into 1 by 1 plus FXF by C alpha f. This is alpha f minus WRU squared by C alpha r into RG into 1 by 1 plus FXR by C alpha r. Right? So this is what now by substitution. So now you look at this term FXF by C alpha f. It's very, very smaller than the value of 1. The factors considering FXF drive force in the front axle by the cornering stiffness of the front axle. If I divide, it would be very, very, very small value, right? Then what? So if this is accounted, I can write this 1 plus fx 1 by fxf by C alpha f this term as 1 minus fxf by C alpha f by the series, geometrical series. In our mathematics, we have studied 1 by 1 plus x can be written as 1 minus x plus x squared and so on, minus x cube and so on by 3 factorial. That series is there. So the higher terms I am removing, so I can consider because of this, this can be written as this. So if I consider like that and I do now account these terms here, and my equation would be changing. So before that, what I will do, I will take here on the right hand side, there is a delta term, left hand side also there is a delta term. Delta term, I should bring it, that stair angle term, I should bring it on one side. I will do that, then I will go in for applying this. So if I do that, it is delta on the left hand side, and this into this factor, if I multiply, that's going to be minus become plus here. So fxf by C alpha f into delta into 1 by 1 plus fxf by C alpha f, right? because this is multiplied for this and that term I have taken it on this side. So I have it like this. And now on the other side, it is 57.3 L by R plus, so this term has gone on the other side. So it's going to be WF U squared by C alpha F RG into 1 by 1 plus FXF by C alpha F minus WR U squared by C alpha R RG into 1 by 1 plus, look at here FXF, here it's FXR, rear axial drive force by C alpha R. So this is how it changes now. So looking at now this term here, I'm going to, there are many assumption and no simplification. So when I say this is very, very small than 1, this 1 plus very small quantity, 1 by 1, I can consider that as 1 itself. So I can also consider this for this way, or it is equal to 1. It's equal to 1. So if I consider this term as 1, this term is 1. Because this is very small value, added to 1 is very small. So 1 by 1 I consider. And a very small value means 0.00 something it would be here, 0.001, or even 1 out of 1% also is very less. So 1% if I add with 1 is 1.01. So 1 by 1.01 is almost equal to 1 itself. Like that I can make an assumption. And this term I can neglect it. Then what would happen? My equation on this side, it's only 57.3 L by R plus WF U squared by C alpha F RG minus WR U squared by C alpha R RG. So these two terms are neglected. On this side, I'll have delta plus FXF by C alpha F into delta. So this term I will rewrite like this. So if I rewrite like that, what I'll get, this would be 1 minus that. So, so this term, I'll put it by red color. So this can be rewritten as 1 plus FXF by 1 plus 1 minus C alpha F, 1 minus this. So I replace this by this with this first one. And if I do that, I multiply this with the first term and the second term. So this term would be Fx F square by C alpha F square into delta. So already Fxf by C alpha F is very small, lesser than, much smaller than 1. And its square ratios are going to be further. So this term can be neglected again. So this is neglected. So what would happen? Now I take this delta out. And inside it is 1 plus Fxf by C alpha F. That side it is 57.3 L by R plus WF U squared by C alpha F RG minus WR U squared by C alpha R RG. So this is that. So now I will be bringing only delta keeping on left hand side, and I will bring it this down on the other side. So it's going to be 57.3 L by R divided by this factor 1 plus Fxf by C alpha F. What is to be noted here is, though the drive forces are in the front and the rear, the front wheel drive force is influencing the first term. There are 3 terms here, it is influencing the first term. And then this term is going to be now plus W F U squared by C alpha F RG by 1 plus Fxf by C alpha F minus WR U squared by C alpha R into RG by 1 plus Fxf C alpha R. Fxf C alpha R. Fxf C alpha R. Just 1 minute. Just 1 minute. There's some noise. Just a request. Yeah, so let's continue with our discussion. So here, just have to get the same expression as per Gillespie textbook. Yeah. Here, one thing you have to understand is when I bring this term here now, divided by this and divide this term here. And here I was neglecting this term, right? Instead, I will neglect this term, effect, and take this. Take this term. So this is fx r by C alpha. This is fx r by C alpha. Why fx r I take? It is more appropriate to account. See, anyhow, the quantity 1 plus fxf by C alpha f or 1 plus fxr by C alpha r can be treated as smaller quantity when you have 1 by that denominator, right? So that's what we made assumption. Dry force by cornering stiffness is much, much smaller than 1. If you take it like that, you can either consider like this or like this one, right? So if this is so, you have it now. When I divide this on this side, see, before that itself here I was neglecting this term, right? I was neglecting this term as well as neglecting this term. So instead, you retain that here it is there, assume that it is there. This is there, this term is there. And when I bring it here, there are two terms, the one I neglected. So it's going to be again square. So it's rather at that time you can neglect one. So I'm retaining it like this. So this is what is that equation number now 5. So in this equation now let me use simple manipulation. So the first term as it is 57.3 L by R divided by 1 plus fxf by C alpha f as it is. And I'm going to change here this as 1 minus in the numerator 1 minus fxf by fx C alpha f. So that's going to be wf u squared by C alpha f rg into 1 minus fxf by C alpha f minus WR u squared by C alpha r into Rg into 1 minus Fxr by C alpha r, right? And in this side it is delta. So now let us again group the term and then now find out. See, this all exercise we do it. What would be the influence of drive force or the tractive force on the wheels generated on the understeer gradient? So I have to write it for that form. So it is 57.3 L by R by 1 plus Fxf by C alpha f plus I'm going to write term KES term now. So KES term, how do I write? First term, I'll take it with this one and this one. That's going to be WF by C alpha F. And here it is WR by C alpha R. C alpha R. So in both of that, I have U squared by RG, which is lateral acceleration, normalized by G, that I will take it out. So that's going to be here. That's U squared by RG, I'm taking it out. Then my second term here would be this into this. So that's going to be minus. There's minus sign here and there's plus sign here. So I have to take minus sign out now. So here it is not plus. it is going to be minus. And this term is going to be WF FXF by C alpha F square. This C alpha F, C alpha F. And minus here, that is WR FXR by C alpha R square into this. So now you look at this equation, compare this equation with our steady state governing equation. What is our steady state governing equation? Comparing this with this equation, delta equals 57.3 L by R plus KUS into U squared by RG. So this is KUS and now this is KUS. The KUS value is given by that. So I have here a term. So there are three terms on this side. Earlier I don't consider, now I have to consider this also because this has got some implication. So this is term 1 because this is been now altered. The Ackermann steering angle is getting now changed because of the drive force that are acting on the wheels. So it is be divided by this factor that I have to consider. And this term is term 2. This good old understeer gradient alone considered from the tire compliance. And this term is term 3 that's coming from tractive force. So FXF and FXR is present here and the cornering stiffness is also there. So these are the three terms. So now this is how you can derive the effect of understeer effect on understeer gradient due to tractive forces acting on the tire road interaction. What is to be remembered here? You may wonder what happened to camber change effect and no lateral load transfer effect all. We are not taking all. So if we are accounting all of them and we are trying to work out, we would be having a very long equation. We get that become cumbersome process. That is why we state the assumption clearly of the model description clearly, and then we go in for deriving the requirement of this. So in this, if I account suspension, if I account camber, whatever that we have got, it all can be proven. But for the convenient, I don't consider suspension. Again, I have taken bicycle model. In my bicycle model, I just have introduced drive forces. And thus drive forces effect is what we have studied and derived. So now let us look at and interpret more on this equation from these terms. Right? So the term 1 here is what is the influence of this term 1. So what is that? You have to understand this. This is the Ackermann steering angle alteration. What is the Ackermann steering angle is altered by tractive force on the front axle. The rear tractive force does not show up here. That doesn't come. So FXR doesn't come. So this is an influence over. So tractive force effect on Ackermann steering angle. Ackermann double N. Sometimes this one steer angle. Some textbook double N, some book it is only one N as well. So this is that effect. So now you can see if I have more drive force, if I do accelerate, what would happen? Whatever my Ackermann steering angle originally there in steady state motion, get influenced how? If this is positive, tractive force is positive. So FXF is positive means what? It refers to traction applied. So this term is getting added with this one. So this denominator is going to be more than 1. And this is going to reduce this Ackermann steering angle. So there will be reduction in Ackermann steering angle. So if FXF is positive, drive force applied on front wheel drive. So if I have front wheel drive alone, I'll have this term, right? Front wheel drive. So that would reduce the steering angle. So that would reduce the steering angle. So if FXF is positive, delta is reduced. Not delta, Ackermann steering angle is reduced. Delta Ackermann. Right? Ackermann steering. So Ackermann steering means this term would go 0 when it is neutral steer effect. Then we will have only this. So that this is brought down. So the steering angle part from Ackermann. So I just call this term as now delta Ackermann. ACK, I just put subscribe. So this term brought down. And that would account the sense that the forward wheel drive pulls the vehicle around the low speed maneuver, even at low speed maneuver. Correct? Ackermann steering geometry is what we have looked at in low speed cornering, and it will pulls the vehicle around the low speed maneuvers. That's the meaning. Then if FXF is negative, when can FXF is negative? When it is braking force or steady state motion only, but I have my rolling resistance force, which is always negative. If that comes, what would happen? This term is going to be smaller, and that would bring in a steering angle more. If FXF is negative, maybe that represent rolling resistance force. Then delta Ackermann part would increase, right? So this is what is that way you can interpret. So you can also look at when front wheel spin on snow or ice. So we know very icy surfaces are front wheel spin. So the front wheel drive vehicle and you are starting the vehicle, rather the vehicle translate, the wheels are spinning. That is called 100% slip. That's why it is spinning. So what do we mean by that? Is that the tractive force still produced, but C alpha F goes to 0. So if wheels are spinning on icy surface, then what would happen? The tractive force is produced, but it is not moving. Why? Because C alpha F goes to 0. That's the meaning. When that goes to 0 here, what would happen in this term? Term 1. If this goes to 0, denominator, this is infinity. So this entire thing is infinity. This is going to be 0. So when this is going to be 0, Ackermann steering angle is 0. What does that mean? What does that mean? In that case, the denominator of the term becomes infinity. Denominator of that become infinity, suggesting that the turn of 0 radius can be made with virtually no steering angle. This accounts for the trick for turning a front wheel drive vehicle within its own length on the icy surface. So the icy surface you see in movies, you could see that when slippery road, no, when the vehicle spins there, and that is because of this effect. So that's what you would be saying. If this tractive force is not there, steady state motion is a safe motion that we have studied. Once the tractive force, drive force comes here, this term Ackermann steering geometry changes. That would influence even at low cornering, low speed cornering. That's what we have seen from first to two. And here, when can that be? 0 is when the icy surface, the slip which we are going to study again in our pneumatic tire mechanics, separate module tire dynamics, we'll look at it in detail. You'll have this term goes to 0, then the denominator of your first term is infinity, and that shows an Ackermann steering requirement is 0, and that is the trick what is used for spinning of your vehicle within its own length. That's what is that you should understand. And second term is very simple. Term 2. Term 2 is what its tire compliance is. Compliance itself. What you have already studied. That I don't require to explain. Look at the third term. So third term, so this gets subtracted. There's a minus sign here. So if I do not have this, I'll have only this. So if this value is positive, this value is positive, the difference you have to see. If this entire quantity is smaller than this, still it is understeer. If this quantity is greater than this quantity, tire compliance, then this is going to be minus. So that is oversteer tendency. Right? If this quantity is negative, then this minus minus become plus, then the vehicle become on understeer vehicle itself. That is what is the storm 3 influence. And let us look at now. If I have front wheel drive vehicle, this term will not be there because this is confining to FXR, that's 0. If I have rear wheel drive vehicle, then this won't be there, right? So if it is a rear wheel drive vehicle, if this term is not there, this minus and minus become plus. I'll get already this is positive of the vehicle and this get added, so that is understeer, more of understeer vehicle. If it is front wheel drive vehicle and this is not there, this term is not there, I'll have this term, but this term is smaller than this, then it is an understeer vehicle, right? This is KES positive, I consider. If this K is positive, then it is, if this is 0, it is subtracted. So this would be having a tendency to go into 0 and then a negative. If this value is negative value means what? When you are braking, this is going to be FXF is negative. So then this become positive, then what will happen? It will become more of understeer effect. So like that, you should interpret the third term. Term 3, right? So if you have any doubt, you can ask. This is to see how understeer changes to oversteer, or oversteer further to oversteer, or KU is going to 0. So when KU is going to 0, term 3 equals term 2. So when this term is equal to this term, then it is a neutral steer vehicle, right? So this is all something that we can interpret in a real-time vehicle. This simplified assumed models, and that completes an important part of lateral dynamics, that is with reference to a directional response, directional control, and so on. And yet we have to look at vehicle stability. So we have to look at stability of a vehicle in a yaw plane, that is on the ground. That vehicle, when it will be going to spin. When you drive a vehicle, suddenly you have to take a turn, you corner it, but what will happen? The vehicle go unstable at a critical speed. That is what is unstable state. So you will not have a steady yaw velocity. Instead, a drastic yaw acceleration can happen, and that would lead you to an unstable state. So what is the condition? How can we limit that? All we will have to study. And then rollover stability problem. So when you consider suspension, there is a lateral load transfer, but the lateral load transfer will not make the equilibrium of your vehicle disturbed, but it will be disturbed the moment there is a limiting value of lateral acceleration. And if that happens, then the rollover cannot be prevented. So how can you quantify or understand that physics? Is what is left in stability part. After that, we have tire dynamics alone. Of course, there is no explicit mentioning of longitudinal dynamics in your syllabus, but we are going to look at longitudinal dynamics as well, at least for acceleration, braking, and gradability means what. So 1 or 2 lectures we have, and that is how our syllabus in another 15 lectures would be getting over after your CAT 2. So I stop at this point of time. And you have looked at an understeer gradient change from its steady state motion due to various other factors other than tire compliance. One is lateral load transfer, another one is roll steer effect, another one is camber effect, can change in camber. And today you looked at what would happen if drive forces are acting or brake forces are acting, change in KES. And you also have like that, if you in the list, there's something called a lateral force compliant steer that comes from the bushes in the connections of your suspension. That would create a kind of lateral force. Like lateral force developed at the contact patch of tire and road interaction called tire compliance. You also have NVH purpose. The bushes in the linkages would be there. That would have some lateral force, and that can also cause kind of a steer effect. That's what is called a lateral force compliant steer. So there can be an expression. You can look at it in the Gillespie textbook, and you have to account your self-aligning torque. We'll look at study that what is self-aligning torque again in our tire dynamics, and that's going to again always give an understeer effect for your vehicle. Because any steering tendency would be resisted by your self-aligning torque, as there is a term called a pneumatic trail that comes into contact patch. And that is the line where your lateral force is acting just behind the center of the contact patch, and that would create a moment called the self-aligning torque. We'll see that in detail. So that is also going to contribute some influence on this understeer effect coefficient, and it will be always get added to understeer gradient. That's positive value, right? And you also have some steering system and its compliance on the KUS influence. So these all are something. The formulas are given in the textbook. Please go through them. And here is where I stop our lecture. If you have any doubts, I would be happily answering. Otherwise, we will end the lecture. So no doubts. I will stop.